Hello, everybody, and welcome back. Today, we're going to be talking about deletions using our linked nodes, our linked list here. We are going to start off by sort of discussing this through a scavenger hunt analogy. Imagine running a scavenger hunt where each clue tells you where the next clue is hidden. But what happens if you want to remove a clue? Maybe it turns out it's not such a good clue, or it doesn't really move your story forward. Today, we're going to learn how we can safely throw away that clue without ruining the whole rest of the hunt. Let's just start with the easiest one, which is going to be to remove our first clue. Now, before we do that, I did have to set up some code. I'm going to just walk through it really quickly. If you want the deeper dive into what all this code means, please see one of my earlier videos. So I have my node class. I set it up with 2 nodes. I have my constructor where I pass in the data and the next node. I also have an overloaded constructor here with just 1 parameter where we pass in the data. It uses this constructor, as you can see, just by passing in null directly. So I have 2 different ways of initializing nodes. I have my getters, I have my setters, and I have a toString right here. Up here in my functions, I have my initialize list where I'm just adding everything to the top. I wanted them to be in increasing order just to make it a little bit easier when we're viewing our list. So I'm going through my for loop from 10 all the way down to 0. Since we are inserting at the top, we're kind of pushing our list down as we go. This is how we're going to get that ascending numbers list. I've also already written my print list right here. It prints out the current list, and then it's going to go through every single element, printing each one out. As long as we're not at the end, I also get that arrow. We can see that this works right here. We get our list from 0 to 10, exactly as I'd expect. Now that we have a started list, we can start with our deletion. The head of our linked list, that top element, is the first clue that we would technically hand to a player. Top.data, right? If we don't want that clue anymore, that's no problem. We just hand them the second clue instead of the first clue. Let's go ahead and look at what that means. We would make a function delete top, and let's take a look. Public static node delete top. Node top. So if we have a list, top is going to start us off at clue A. Clue A points to clue B, which points to clue C, and so on, all the way until we have the end of our list. How do we make top not look at clue A, but instead look at what clue A is looking at? So at the next one, well, it's actually really simple. Let's just return top.next. That's all there is to it. And now if I try to print my list, what we will see, top.getNext, pardon me. Here we go. We'll just get that cleared up. Is we've removed 0 from our list. Now we do have a scenario here that we're currently not thinking about. Imagine for a second that we did this for in I is equal to 0, I is less than 10, I plus plus. We want to remove, I guess I is less than 11, all of the elements. And then print. Let's see what we're left with. Our current list is empty. But what happens if I try to delete top from an empty list? We are going to get a null pointer exception. We cannot delete from an empty list because if top is null, you cannot say null.getNext. That means we need to take care of this scenario of if top is null. If top is null, we just want to return null, not the next one. Now you could write this in an if statement. I'm just going to use a ternary operator to make my life a little bit easier. If top is null, just say null. Otherwise, get the next one. I just wanted this to be in a nice single line. Now we can see my code no longer explodes. and I'll get 2 empty lists printing out here with no explosions. So anytime we're modifying our linked list, it's really important we're doing that check for null. So as we saw, we're not actually ripping our clues out of the ground. We're not actually changing the clues' physical locations in the scavenger hunt. Clue 1 still is floating around out there in the world. We're just changing which clue we're handing out to our top. Which clue is getting handed out first. Once clue A is gone, garbage collection in Java will come and take care of it, but the rest of our chain will stay intact because clue B still knows where clue C is. And that holds true for our list example here as well. What we will find though is that removing clues in the middle of the hunt does take a bit more navigation. The good news is removing clues from the middle of the list and removing clues from the end of the list are exactly the same. So there's really only 2 cases that we have to worry about. Removal from the top and removal from the middle. To remove a clue from the middle, you don't go straight to the clue that you want to delete. You have to imagine for a second that in order to delete that clue, you have to actually go to the clue before it. Because if we look at our example with clue A still being intact here, clue A, if I want to remove clue B, I have to actually change clue A's navigation so that instead of going to clue B, it's going to go to clue C. That involves changing clue A's information, not changing clue B's information. If I change clue A's information so that it bypasses clue B, nobody cares about clue B anymore. Nobody will see it. It can still reference clue C. It doesn't matter. It doesn't change anything. Even if clue B is still looking at clue C, when this method ends, garbage collection will come along and pick up that garbage and get rid of it for us. So that's no problem at all. Now, there are 2 different ways that we can do deletions. We can do deletions by index or a deletion by search. Each one comes with its own challenges of index out of bounds or elements not being found. Let's start with the idea of delete at. Public static node delete at. This one is going to be a deletion by index. Int index. Now, if our index is 0, let's see, node, we can just do it like this. If our index is 0, top is actually just going to be, become equal to the delete top method. We already have a method for that, which is fantastic. Else if our index is less than 0, meaning a negative, we'll do what we did last time, which is throw a new index out of bounds exception. Negative index is not valid. Next, we can look at the more standard case, which is our actual deletion from somewhere in the list. So we can say int position is going to be at 0. And while our position is less than, and remember this from our video in adding in the middle, we need to go to index -1. We also need to consider the situation that cur stays valid. Node cur will start at top. While the cur position is not null and we're not yet at the correct index, let's walk through our list. Position ++. Awesome. At this point, if cur is null, we fell off our list and we didn't actually get to the end of the list. This is the condition that we broke out of. We can also consider the situation where the next one is null, because technically the next one is the one that we're supposed to be getting rid of. But if the next one is also null, there is no data there to delete. I would say to remove, but to delete. So in both of these scenarios, we are throwing another index out of bounds exception. That index, whoops, I should make that a string literal. That index, whatever it was, whoops, is invalid because it's too big. There we go. Don't need that many O's, I suppose. Awesome. Now, if we've managed to pass all of these checks, nothing is negative and we haven't fallen off our list, then at this point in time, we can do our official deletion. Now, we know that our current node is the one that we now need to connect to the rest of the list, ignoring the target to remove. The target to remove is cur.getNext. The rest of the list starts at target to remove.getNext. So our current element needs to be connected to the rest of the list. Perfect. Once we've gone ahead and done that, we should now be good to return our top. A reminder that if we pick an index like 0 that affects our top, we will reset our top node. If we pick an index that does not affect our top, no problem. It will be automatically propagated through thanks to the way that our scavenger hunt and references work. If we change something in the middle, the first node can stay the same. Our first scavenger hunt clue doesn't need to change. It will still lead to the second, and the second will still lead to the third. But now, if we deleted the fourth, the third will just lead to the fifth. No harm done, no need to change what our first clue ever was. If we're updating B's clue, instead of saying go to C, we're just rewriting it. We're saying go to D. This one is remove C. This one says D clue is here and onward. And this says B should go to D. Let's test this out before we move on to delete by value. Let's go right back up here. Let's just make sure that we have a nice, clean, fresh list. Everything is still working as expected. Perfect. Let's go ahead and do a delete at. Let's start with a delete at 0 and make sure that that still works as we'd expect it to. I'm going to just add a print statement here that prints the command that we're running before the print, just as a way to help us keep track as we add more and more things here. Oh, whoops, need a semicolon. Perfect. Let's clear this mess out of the way and run. Here was our original list. Then we ran delete at top 0, and we can see that 0 was indeed deleted. This was deleted by index, so it deleted index 0. Now, this might get a little bit annoying because we're about to discuss delete by value. So I am actually going to just very quickly change my list initialization here to be multiples of 10 plus 1 instead. This is just going to make it a little bit clearer so that when we start deleting by value, we have a difference between value and index that's a little bit more discernible. Now when we delete at index 0, it removed the value 1. That's just going to be a little bit clearer, I feel like, going forward. All right, let's move this down like this, and let's move on to public static node delete by value. This will still take in our node as well as the value that we want to delete. This is going to be a target value. Awesome. Now, there's really only a couple of things that can happen here. Deleting by value means find the first clue that says X and then remove it from our hunt. So for example, if we had a clue like this, 5 that led to clue 7, that led to clue 9, that led to a different clue 7, that led to a clue 12. If we said, find the clue that has the value 7 and delete it, it will find the first value 7 and delete it. Using it as clues makes a little bit less sense for deleting by value, but deleting by value does lend itself a bit more naturally to what our brains understand. So hopefully the intuition is there just a little bit more by default. It's going to be the first clue that contains the value, the message 7. If the first clue contains the value, we don't need to update anybody. We just need to hand out the next clue instead, similar to delete at 0. So if we find it in that very first position, we're going to need to delete it accordingly. Let's take a look at that example. If top.getData is equal to our value, then we just delete our top element. Just like we had before, we're just getting rid of that first one. Very straightforward. If that's not the case, we're going to consider other scenarios. Consider it is elsewhere in the list. And then we'll return top. Let's start with this scenario. I'm going to remove this code from up here since we're not going to be doing those deletes anymore. Instead, let's do a delete by value. And we're going to delete value 1 because we can see 1 is going to be that top element. Let's set this up just as we did before with this printing out so that we know what we're running. Let's clear out this mess, recompile. Oh, whoops. Did I not make a get data in Node? Oh, I didn't. You know what? Instead of making a get data, I'm going to do better with my encapsulation, and I'll make a new method is equal. And I can pass in a node, and in here, I'll just check if the data is equal to this data. There we go. And now, instead of saying top.getData, I'll say top.is is equal to this value. That's an int, not a node. Silly me. Int n. There we go. Now I can compare them without exposing the data outside of my node class. So top.is is equal to value. Let's try this again. Perfect. And we can see that we did delete by value. 1 was found and the list was returned appropriately. So everything so far is working as expected. Now, before I move forward, there's one more case we need to consider here, which is what if top was null? I'm just going to hard code top being null before we go forward. What is going to happen? Well, we can't say null.is equal. So as we know, we're going to get a null pointer exception. Cannot invoke node.is equal because that top node is null. So we also have to have this scenario figured out as well. If top is null, do nothing. Top stays null. Else if. This is one way to write it. We could also write it by negating, this. If top is not null, let's look into the different scenarios. So this ensures we don't have an empty list. Awesome. Let's now consider elsewhere in the list. Now, even though we're not going by index, we need to approach this in the same way, which means if I want to delete this 7, I need to stop at 9. So I always need to be looking 1 ahead. Let's go ahead and get this written. Node cur is equal to top. We always have our helper method. While our current.getNext is not null and our current.getNext is not equal to our value, we need to keep going through our list. So we're going to keep going through our list until we're at this position of either our next is null and we didn't find it, or the next is equal to the value. If our next is null, that means we didn't find value in the list, like the element value, not like value worthiness. What can we do in this scenario? Well, it might be nice to print out a message. We could say the value, whatever the value was you were looking for, was not found. Some like built-in lists might actually throw some kind of an exception, like missing value, value not found, something like that, but some might not. And then we can just return top. That's all there is to it. If, however, the current.next is not equal to null, meaning there is still an element there, we must have stopped for another reason. The only other reason that we would have broken out of this loop is because they were equal to each other. Now, if you want to be extra safe, you could always do another check in here, but I don't think that it's necessary. All we need to do now is make those helpers. Node to delete is going to be cur.getNext. And node rest of list is the deletion node .getNext. And now we can take our current node and set its next, instead of to delete, to the rest of the list. At that point, we're done and we can just return top. Deleting by value is like scanning each clue until you find the one with the unwanted message. And when you do, you grab that clue before and you rewrite its directions so that the hunt continues past the removed clue. Let's go ahead and give this a try. Top will be equal to delete by value. Let's try and delete 61 from the middle. Top 61. We're going to add that print statement and that whole print after, just so we don't get too confused about what we're looking at. There we go. Clean this up and run. Oh, whoops. We left our top equals null overwrite in from when we were practicing things. Let's remove that and try again. There we go. So first we delete 1. We can see 1 is gone. Then when we delete 61, our list got shorter, but it didn't get removed. 21 got removed. This is actually a really tricky error to figure out just because of how I coded it up. And it's just missing one of those really small things. But it's okay to make these kinds of mistakes. And it's honestly probably a good thing that I did to allow me the opportunity to show you how to debug this. So within this method, we can see that 1 was removed correctly. Let's clean this up a little and we'll make it bigger. So we can see that 1 was removed correctly after we called on this 1. But then when we try to go remove 61, we can see that that didn't get removed, but also the top didn't get removed. The second one got removed, which is exceptionally interesting. So if we look at our code, we can see very quickly why this happened. This happened because when node cur equals top, it started at 11. And then cur.getNext was not null, it was 21. And cur.getNext is equal to value. It's not equal to value. So it broke out. I am missing a not. I'm missing a single exclamation mark to say, wow, we haven't found the value yet. That's all we're missing. Something really, really tiny messed all of this up, and something like that can take a really long time to figure out. I'm glad I was able to catch it really early. Here we go. Cur list 61 has now been removed. It's no longer there after we've called our delete value 61. In addition to small logical errors like that, there are other really common pitfalls. Some I've already mentioned, like forgetting to update our head, which I've done already in previous videos, overwriting next too early. So this is like writing a new direction onto a clue before you've read any of the old directions. If we erase them too soon, we won't know where the other clues are hidden. That's why I really like to make these extra variables here when I'm doing this overwrite. If we forget to check for null, we get those null pointer exceptions. Or if we try to delete from an empty hunt, which kind of ties in to that checking for null. When we're doing our scavenger hunt in real life, we'd always want to find the clue before the one that we're removing. If we can't do that, we don't know which clue we actually need to rewrite. We want to make sure that we find it, we read its directions, we update it carefully using the clue that we're trying to delete's information, and then we can safely discard it. If we do this out of order, everything can fall apart. So deleting a node is simply updating the node before it so that we skip over the removed node. And that's it. It's one reference change. We don't have to make a bunch of different variables if we don't want to. There's no magical destruction. We're just rewriting a single direction. We just need one of our references to say where to go next in memory. And that's all there is to it. Keep track of your references like clues in a scavenger hunt. When we do this, our linked lists will always stay intact. That's all there is for this video, and in the next one, we're going to put all this together and raise it one level up in abstraction and truly make a completed linked list class. Thanks everyone, and I'll see you there.